Hey y'all, this is going to be a video on a colligative property question that I put on an exam one year, and I'm going to go through it step by step and we'll do all of our considerations for colligative properties. This also has a little bit of the chapter on liquids and miscibility in it, so we'll start there. If you've ever baked something and you wanted to flavor it strawberry, you can go to the store and you can buy cheap strawberry extract. And what that is actually a solution of ethanol. And this chemical, which is shown here, called ethyl methyl phenyl glycodate. Practice it. I will give you the molar mass if you have something this large. This is quite a bear. And I especially wouldn't ask you to do this just by looking at the picture and trying to calculate the number of carbons, because you certainly could miss one. When I gave this on an exam, I asked my students to tell me which parts of this molecule have nonpolar or polar characteristics. And then secondly, is it soluble in water? For this second question, is it soluble in water, I am less concerned with you nailing the exact right answer and more concerned with you being able to explain what your conclusion is. So, when we look at this, you do have to remember that we're working up in the world and we've been looking at different depictions of molecules. And this depiction has a little bit of shorthand in it, not a lot. It does show all the hydrogens, but the carbons are... Actually, let me put this in a different color. We have a carbon here, carbon, 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 carbon. Right? So traditionally in organic chemistry, where you have a corner, you have a carbon. So when I look at this molecule and I think about, well, is this polar or nonpolar? I see a couple things. I see oxygen, oxygen, oxygen. And I know that oxygen has a fairly high electronegativity, and I might expect to be able to draw some polar vectors here. Right. I also might recall that in most Lewis structures, when oxygen has these two bonds, it also has two lone pairs. You can do the counting. You certainly can imagine what this looks like just for an isolated oxygen for the Lewis structure, because you're given the number of bonds, right? You can chunk this structure up and start to think about, well, what does just this area look like? So I would conclude that there is some, and I'm going to do it in blue, polar characteristics in this region and here. And then I look over and I see, what is the rest of the molecule? The rest of the molecule is carbons and hydrogens. It is carbons and hydrogens all over. And I know that the carbon-hydrogen bond is not very polar. And what's more, a lot of these areas have quite a lot of symmetry. So I know even if there was a lot of polarity there, some of that's going to cancel out. So I'm going to go ahead and highlight all the non-polar areas in purple. And there is a big old benzene ring in here, which is not very polar at all. So I look at this and I go, okay, overall, this has some polar characteristics, but it's more non-polar. So I might conclude that it is not soluble in water, or at least not very soluble. And that, in fact, is the right answer. It is not very soluble in water. Now, if you had given me an explanation of why you thought there was enough polarity here, or you said there's a big region of polarity in the middle, I think it might be soluble in water. As long as your labeling is correct and you've identified your polar and nonpolar regions and your reasoning makes sense, I would probably be okay with that for the purposes of the general chemistry exam. Some of these things are not always obvious, but you should be able to break down a molecule into its polar, nonpolar parts and make a good, well-founded guess of miscibility. That's about what I'm asking for. This goes on, in the exam I gave this on, to say that you are going to prepare a solution with ethyl methylphenyl glycidate, and it is going to be made of 103.1 grams of your strawberry flavoring, and you are going to use 750 grams of ethanol to do it. And I will give you the molar mass if it's a large molecule like this. In most cases, what is the molality of the solution? And this should be a clue. If I'm asking about molality, you can expect that I'm probably going to ask you about one of the colligative properties that calls for it. So freezing point depression or boiling point elevation. And you will need to remember that the definition of molality is mole solute over kilograms solvent. Solvent, not solution. A little bit of nuance here. I do give you the mass in grams. I tell you we have 750 grams ethanol. That's just a little shorthand for ethanol. And that is equivalent, because there are 1,000 grams in a kilogram, to 0.75 kilograms ethanol. Now, that is half of what you need for molality. Check. Now you need moles. So that's just a classic conversion. You have 1.3 grams. I'm not going to write out ethyl methylphenyl glycidate. I just simply don't have the screen space. I'm going to call it flavor. This is, at least in the case of this hypothetical solution, the only flavor at hand. So just to save space on my notes, that's how I'm going to do it. You can always keep track of your units, just like that. And this comes out to, you might be able to see it without punching it into a calculator, half a mole. So we can plug this in. We say the molality is equal to 0.5 moles of our compound, which provides this sort of artificial strawberry flavor, over 0.75 kilograms of our solvent, which is ethanol in this case. And I can say that we have a molality of 0.667 molal. Now, this will be an important number to carry forward into the next part of this problem. So now, in this exam, I started asking about the change in freezing point. And this is something where you need to remember the direction of the important colligative properties: vapor pressure lowering, freezing point depression, boiling point elevation. I do go ahead and give you the KF. You certainly would have to look this up on an almanac or something. There's no way to just know it. And I will give you the freezing point of reference. You also would have to look that up in an almanac, and you can't just know it. Now, this will be on your formula sheet, but it's not a hard formula to remember. We have the change, remembering that delta means change, in the freezing temperature is equal to this constant KF, which is given to you, times the molality of the solution. Sometimes this will be written this way to take into account Van Hoff factors for ionic solutions, where when you dissolve 1 mole of something, you might get 2 moles of particles or 3 moles of particles, depending on the stoichiometry. This is a molecular solute. You should be able to recognize that by looking at the formula on the front. It's molecular, so it's not going to have a Van Hoff Van 't Hoff factor other than 1, so I'm not going to use that version. I'm just going to keep with this one. I'm totally happy with it. And I'm going to say the change in the freezing point is going to be equal to 1.99 degrees Celsius per molal. And we already calculated the molality, 0.667. And you can go ahead and punch that into your calculator. And you should get something like 1.33 degrees Celsius is what the change in freezing point will be. Now, you cannot stop here because you have to remember these relevant directions. Do not tell me that the freezing point is 1.33 degrees Celsius. First off, that's so far off from the number I gave you. And secondly, that's not even freezing point depression, right? You're in the wrong direction if you do that. So you have to remember that the new freezing point is equal to whatever the old freezing point was, minus the delta T that you calculate. And I will always give you these constants as their positive values. That's the format that I like in the books I use. I think it's better to remember the direction of the colligative property than it is to rely on your almanac, including the directionality for that constant, because in my experience, some do, some don't. So negative 114 degrees Celsius minus 1.33 degrees Celsius. You should have a new freezing point of negative 15.3 degrees Celsius for your ethanol that contains strawberry flavoring. And you must remember that you have freezing point depression, and then you can check yourself. This makes sense. The freezing point is more negative. It's gotten lower, so we can feel good about this.